This video covers section 7.3, Simplifying Radical Expressions for Math 95 at Linn-Benton Community College. Our goals in this section are to use the product rule for radicals, the quotient rule for radicals, and generally to simplify radicals. If you happen to be reading along with your book, notice that we're not going to cover the distance and midpoint formulas, but that's okay, they won't be on your test. Before we jump into these rules, I want to see if I can jog your memory about simplifying radicals. For instance, something like the square root of 72. Do you maybe remember factoring 72 to see if there were any perfect squares in it? For instance, 72 factors into 4 times 18. And then that 18 factors further into 2 and 9. We could even continue factoring that 4 to be 2 times 2. That meant that the square root of 72 is the same as the square root of 4 times 9 times 2. But we know what the square root of 4 is, and we know what the square root of 9 is. So that became 2 times 3, but there was still a single 2 left over stuck under the square root. And at last we simplified this by multiplying the 2 and the 3 and making that 6 times the square root of 2. Some students like to factor the number under the radical as much as possible and then think about pairs of numbers that can get out from under the radical. Here I had a pair of 2's, which turned into a 2 out here, a single 2, which didn't have a pair, so it was stuck underneath the radical, and then that 9 was a pair of 3's. So that came outside the radical. Anything that didn't have a pair stayed underneath the radical. Now, if this doesn't look too familiar, don't worry. We're going to talk about it in more depth. However, you may have seen something like this, for instance, in our Math 65 class. If so, we're just going to be building on that skill that you already have. The big idea is that as long as we have like radicals, we can multiply and divide them to help us simplify expressions. In math terms, we say, if I have the nth root of a times the nth root of b, I can push those together to be the nth root of a times b. With the division part, we say, if I have the nth root of a divided by the nth root of b, that would be the same as just the nth root of a over b. So all those a's and b's and n's can be kind of confusing. Let's take a moment to try to put these two rules into plain English. So I might say if two radicals of the same type are being multiplied, we can do the multiplication underneath the radical first and then do the radical. Or if two radicals of the same type are being divided, we can do the division first and then do the radical. Another way that I might describe this first one is that it doesn't matter whether you do the multiplication or the root first. You can take the roots and multiply, or you can do the multiplication and then take the root. Similarly over here, it doesn't matter if you do the roots or the division first. You can either first take the root of each thing and then divide, or you can do the division first and then take the root. It's almost like a little loophole in the order of operations, where as long as it's the same type of radical and we're doing either multiplication or division, you get to choose which one you want to do first. Now, those are just some of my ways of interpreting these two rules. You should feel free to explore other resources and find something that works well for you and sticks in your mind. Remember that you can use each of these rules two ways. You can start with two radicals and then smoosh them together to get one radical, or you can start with one radical and pull it apart into two radicals. Each direction there will be useful at different times. All right, a final note before I move on to some examples. If we don't have radicals of the same type, these rules don't apply. However, you could still convert those radicals to rational exponents like we did in section 7.2 and do the multiplication or division that way. All right, it's time for some examples. I'm going to simplify each of these three expressions using those rules of radicals. This first one is the square root of 3 multiplied by the square root of 7. Because they're both square roots, I can rewrite this as the square root of 3 times 7. Now I do know what 3 times 7 is, that's 21, so this becomes just the square root of 21. Notice that if we factor 21, there's no perfect squares, so this can't be simplified any further. Next up is the square root of 18. This time we're going to want to use the rule going the other way to pull this apart into two radicals. Our real goal is to pull it apart into two radicals where one of the radicals is some nice number. For the square root of 18, that's going to mean factoring 18 into 9 times 2. So that becomes the square root of 9 times 2, which is the same as the square root of 9 times the square root of 2. We chose this particular factorization, 9 times 2, because the square root of 9 is a nice number. So this becomes 3 multiplied by the square root of 2. Now, if you didn't happen to notice that 9 times 2 was going to work out nicely for us, there are some tricks to being able to see that. You can start with your 18 and then factor it as much as possible. So maybe you start by noticing that 2 goes into 18, which gives you 2 times 9, and then 9 factors into 3 and 3. Now, because this is a square root, we're looking for pairs. We're looking for perfect squares. 3 and 3 make a perfect square of 9, whereas that 2, that's all by itself, doesn't make a perfect square. So because there's a pair of 3's, I end up with 1 3 on the outside, and since the 2 didn't have a pair, it winds up stuck on the inside under the radical. My next example is the cubed root of 27 over 8. This time I'm going to use the quotient rule to split this up into two radicals, the cubed root of 27 over the cubed root of 8. Now each of those is something that I know. The cubed root of 27 is 3, and the cubed root of 8 is 2. So it gives me a nice answer in the end. Now it's your turn to practice. Go ahead and pause the video, try each one of these on your own, and then when you start the video up again, we'll look at them together. All right, are you ready to look at these problems together now? I started with the cubed root of 40. I started by rewriting that as 8 times 5. So then I had the cubed root of 8 and the cubed root of 5. But the cubed root of 8 is a nice number, 2, whereas the cubed root of 5 doesn't have anything going for it. So it just stays the cubed root of 5, and my final answer is 2 times the cubed root of 5. Now, I happened to notice that 8 times 5 would be a convenient factorization of 40 in this situation. If you didn't see that, however, you can always get the prime factorization of 40 and figure this out anyways. So down here I wanted to show you that I found the prime factorization of 40 to be 2 times 2 times 2 times 5. Notice that this is a cubed root and not a square root. So when I'm looking for something that can escape to the outside, it needs to come in a group of 3. Here I have 3 2's, so I end up with 1 2 on the outside, but only a single 5, so that 1 5 stays on the inside. Or you can notice that this is a nice group of 3 2's, which means that 2 times 2 times 2 is 8. 8 is going to be something nice to factor with. Next up is the cubed root of 2 times the cubed root of 32. Because these are the same kind of root, we can push those together to become the cubed root of 2 times 32, which is the cubed root of 64. Now that happens to turn out as a nice number. The cubed root of 64 is 4. Just for example's sake, I wanted to go ahead and show you what would happen if I tried to find the prime factorization of 64. I found a whole lot of 2's. The important thing to notice, though, is that I have 2 groups of 3. Because I'm looking for a cubed root, I'm interested in groups of 3. Under the cubed root, this group of 3 2's translates to 1 2 on the outside, and this group of 3 2's translates to one more 2 on the outside. this 2 times this 2 is that 4. Our last problem was the square root of 6 over the square root of 24. On this one, I pushed the two radicals together to get the square root of 6 over 24. And then I noticed that 6 over 24 can be reduced to be the square root of 1/4. The square root of 1/4 is 1/2, since 1/2 multiplied by itself is 1/4. Or you could notice that the square root of 1 is 1 and the square root of 4 is 2. That'll get you to the same place every time. The last thing that I want to show you in this section is that we can do this whole process of simplifying radicals with variables as well as with numbers. In fact, I think it might be a little bit easier with variables. I'm going to start with the square root of 81x to the 5th. Now I'm looking for a square root, so I'm looking for groups of 2. I'm going to break this x to the 5th up into as many groups of 2 as I can. I'll have an x squared, another x squared, but then I need one more x to round it out so that I have all 5 x's that I had originally. Now we can see that the square root of 81 is 9, the square root of x squared is just x, and the square root of this x squared is also just x, but this x is stuck on the inside. So I have a square root of x left over. I can simplify this down a little bit more by writing it as 9x squared times the square root of x. I'd like you to notice that the 5 here divided by the 2 from the square root gives us 2 with a remainder of 1. That will always work. If you take the power of the thing on the inside of the radical and divide by the type of radical that it is, the number of times that it goes in is how many groups that you'll have on the outside, and the remainder of that division is how many things you'll have stuck on the inside. Let's look at another example, this time with a cubed root. I have the cubed root of 24a to the 9th, b to the 4th. I'm going to work this problem similarly to how I worked the last one, by breaking this down into groups before I take the radical. Remember that I'm doing a cubed root, so this time I'm looking for groups of 3. 24 is 8 times 3. That 8 will be useful since the cubed root of 8 is 2. If I start breaking this a to the 9th up into groups of 3, I will have an a cubed, another a cubed, and another a cubed. And that takes up all 9 of them. For this b to the 4th, if I start pulling out groups of 3, I can get a single group of b cubed, but then there's still one b left over to bring it up to the total of 4. Now that I've broken everything apart, I'm ready to actually take the cubed root. The cubed root of 8 is 2. The cubed root of this a cubed is a, of this one is a, of this one is a. The cubed root of b cubed is b. Now everything that didn't have a nice pairing gets stuck under the radical. So that 3 is still under here, and this single lone b is also still under here. Finally, I can condense this a little bit and make this 2a cubed b times the cubed root of 3b. Let me fix that up here as well. Again, let me show you how you might be able to think your way through to a shortcut from here to here. For the a to the 9th, 9 divided by 3 is 3, which gave me the a cubed on the outside. For the b's, 4 divided by 3 is 1, with a remainder of 1. That gave me one b on the outside, but one remaining b on the inside. For the 24, I kind of had to resort to using those techniques we had earlier. I could have factored that 24 into 2 times 2 times 2 times 3 to see that I would have one 2 on the outside and a 3 stuck on the inside. Now this last example looks a little icky, but I think we can do it. I've got 5 times the cubed root of 162x to the 8th over the cubed root of 3x squared. I see that I have 2 cubed roots, so I'm going to go ahead and push those together and make this the cubed root of 162x to the 8th over 3x squared. But don't forget about this 5. The 5 was in the numerator of a fraction, so that means that I've got the whole thing being multiplied by 5. Now let's work on simplifying the stuff under the radical. I'm going to write my 5 out front just so that I don't forget about it. But inside the radical, 162 divided by 3 is 54. And x to the 8th divided by x squared is x to the 6th. This is starting to look a little bit better already. However, I'm not quite sure what to do with that 54. 54 isn't a perfect cubed root. So I think I'm going to go ahead and factor it as much as I can to see what happens. I notice that it's divisible by 2, and I ask my calculator and find that 2 times 27 is 54. Now you could keep going, but 27 is a perfect cube. It's 3 times 3 times 3. If we did keep going, we would find that 27 factors as 3 and 9, and then 9 factors as 3 and 3. That gives me a group of 3 3's, and since I'm looking for a cubed root, that's exactly what I want, groups of 3. So for my next step, I've still got this 5 out front from the very beginning, but this cubed root of 54 will become 3 on the outside, and a 2 left on the inside. For this x to the 6th, notice that 6 divided by 3 is 2 with no remainder, which means that I will have an x squared on the outside and no x's left on the inside. Last thing, we can combine this 5 and that 3 to be 15 x squared times the cubed root of 2. And of course, now it's time for you to practice a couple. Go ahead and pause the video and try each of these. Don't worry if you feel like you don't completely have it yet. This is another one of those skills that really just takes some practice to get the hang of. So go ahead and pause the video, get some of that practice in, and then come back and we'll talk about these ones together. Okay, did you take a moment to work those problems out? Let's go ahead and look at these ones together. I started with the 4th root of 32z to the 7th. Now, 32 didn't pop out to me as something that I know the 4th root of, so I went ahead and factored it. And I got 2 times 2 times 2 times 2 times 2. Now there's a single group of 4 2's in there, and then 1 2 left over. So I decided to rewrite this first as the 4th root of 2 to the 4th, that's those 4 2's, times 2. And then I broke that z to the 7th down into the z to the 4th times z cubed. Then the 2 to the 4th becomes a single 2 outside the 4th root. The z to the 4th is a single z outside the 4th root. And the 2 and the z cubed are left inside the 4th root. Now my second problem had a fraction with the square root of 80y on top and 3 times the square root of 5 on the bottom. I want to smush these two square roots together, but I have to be a little bit careful that I don't lose track of that 3, which is not in the square root. Because the 3 is in the denominator, I need to keep it in the denominator, which leaves me with a 1/3 out front, and then the square root of 80y over 5. Now, 80 divided by 5 is 16, so now I have 1/3 times the square root of 16y. The square root of 16 is just 4, but nothing good happens with the square root of y, so we leave it as just the square root of y. This is a perfectly fine answer right here, but we can simplify it a little bit more. That 4 square root of y is like 4 square root of y over 1, in which case I can multiply straight across, leaving me 4 square root of y in the numerator, and that 3 still in the denominator. Our last example is the cubed root of 24a to the 9th, b to the 4th. I started by factoring that 24 and found that it was 2 times 2 times 2 times 3, which is a single group of 3 2s and 1 3 left over. I decided to interpret that as 8 times 3. So I rewrote this as 8 times 3 times a cubed, a cubed, a cubed, b cubed, b. So I split these up into groups of 3 as much as possible. Then I took the cubed root of all of the pieces that I could. The cubed root of 8 was 2, and then each of these a cubeds became a single a on the outside. The b cubed became a b. The things that were left on the inside were 3 and b. Cleaning it up a little bit, I got 2a cubed b times the cubed root of 3b. Notice that you really could have gotten here a little bit sooner. For instance, I could have started by factoring the 24, saying I had 3 2's underneath, so I would have a single 2 out here, and a 3 left under this radical. And then a to the 9th, 9 divided by 3 is 3, so that gave me the a cubed on the outside. And 4 divided by 3 is 1, so a single b on the outside, with a remainder of 1 that gives me a single b still on the inside. So you don't really have to write it out like this each time if you don't want to. I hope that gets you started on section 7.3. Good luck with your homework.